What's up, folks? This is Raf Bari, Brown University physics grad student, and today this is the problem we're going to be solving. It's actually really cool, very exciting. It's about a spool of wire that's unraveling and traveling to the edge of a table and thus making a weight drop. And what we have to calculate is the velocity of this weight after the spool of wire has traversed this distance L. So let's get started with this physics problem. What's up, folks? This is Raf Bari. Welcome to the next episode of Classical Mechanics. Now, of course, this is a graduate level classical mechanics course, but what better way is there to start than Newton's second law? Today's problem is going to be kind of trivial. It's going to be an application of Newton's second law in rotational motion, but it's going to really show you the power of physics. Okay, today's problem is going to allow you to predict the speed of an object after a loop of wire has run out, essentially. So let's go ahead and check out today's problem. So in a sense, this problem is kind of like Atwood's machine. As the spool of wire unfolds, the loop of the weight is going to fall down. So as the coil of wire unfolds in that direction, the mass is going to fall down. Okay, so that's the basic picture. Okay, now let me put some parameters on this problem and explain what we're trying to find. So as this coil of wire is releasing over here, this mass is going to be dropping, right? In other words, let's say that this coil of wire is a distance L from the edge of the table, okay? Let's say that this small mass has a mass of lowercase m, this big mass is uppercase M, and this spool of wire has a diameter of d. And what else? What other parameters do I have to give you? Well, what I want to figure out is after this spool of wire moves this distance L, what will the speed of my mass be? Okay, let me frame the problem in another way. So here's my spool of wire. It's a distance L from the edge of the table, and the spool of wire is connected to this weight of mass lowercase m. Spool of wire has a mass capital M, and the spool of wire is going to move to the right. And as it moves to the right, and not only is the spool of wire moving to the right, but the loop of wire is also unfolding, right? And as this is happening, this weight is dropping. So the question is, when this spool of wire reaches the edge of the table, once it has traversed this length L, what will the velocity of this mass m be? Okay, so that's our goal. That's what we're trying to figure out. The velocity of this lowercase m after this spool of wire has traveled this distance L. So after the spool of wire has traveled the distance L, what will the velocity of this lowercase mass be? Okay, so that's the problem. Now we're going to start solving it. The first thing I'm going to do is erase all of this mess and go back to our simple picture here. Okay, so the first thing I'm going to do is write down Newton's second law in all the different ways possible. So what do I mean by that? Well, here's what I mean. First thing I'm going to do is set up a little table here where I have my lowercase mass m, okay? And let's draw the forces acting on m, right? So we have the tension force acting upwards on m, and we have gravity acting down, and we have the tension force acting to the right on our spool of wire as well. So let's draw those forces here. We have tension acting up, gravity acting down. And for our spool of wire, here's my spool, and it has a diameter d, but who cares? I'll write that later. And on my spool of wire, the only force acting, as far as I know, is this tension force due to the rope being pulled, right? Now, here's what I'm going to do. I'm going to make this little table here and write down Newton's second law in all the possible ways. I'm going to write down the rotational version of Newton's second law and the translational version of Newton's second law. So what you see here is force and torque, right? Torque is just a rotational analog of force. So let's apply F equals ma to this one. What do we get? I'm going to get, well, what is helping the acceleration? It's this mg. So mg minus the tension is equal to the lowercase mass times a, where a is the acceleration of this weight. Okay, I'm going to call this thing the weight that's attached to the spool. So acceleration of weight. Okay, great. And what about F equals ma applied to this? Well, same idea, right? I have F equals ma. Now here I've got to be a bit careful. The only F, of course, is the tension force, right? So that's the tension force. What's the mass? Well, this case, this is going to be the capital mass, right? The uppercase M. Now the acceleration is going to be the acceleration of the center of mass of this object. So I'm going to write the acceleration of the center of mass of the spool, okay? Center of mass is simply this center of my spool. So that is my equation of motion. That's Newton's second law for the spool. So I have tension is equal to ma, center of mass of the spool. Okay, now let's take a look at the torque applied on this object. Well, there's no torque, it's not rotating. How about this one? Well, this one's fairly easy. Recall that torque is simply F cross R, right? Force cross radius. Or another way you can write torque is I alpha, where I is the moment of inertia, alpha is the rotational, the angular acceleration. So Fr, what's that going to be? Let me work it out over here, and then I'll replace it over there. So torque is F cross R, right? Now in this case, F is just the tension force, and the radius is going to be the diameter d divided by 2. Okay, and because the tension force is acting at a 90-degree angle, right? Remember the cross product is Fr sine theta, and sine of 90 is simply 1, so we simply have Td over 2. Okay, so that is going to be our tension force, our torque acting on our spool. So the torque acting on the spool, I don't even need a vector symbol here because I'm working in just one dimension. So the torque acting on my spool is going to be 1/2 d times the tension force. And what is this equal to if not the moment of inertia of the spool times the angular acceleration of my spool? There's no such thing as angular acceleration of the center of mass of the spool because the center of mass does not rotate around itself. But the outside of the spool can rotate. That's why I put center of mass over here. I hope that makes sense. If it doesn't, just comment down below and I'll address your questions. So this is everything we have. We've completed our force table over here. Now, force table isn't a real thing. I just made this up to make the problem pedagogically simpler to solve. So now we have all of Newton's second laws over here. Now there's one more equation I'm going to need to solve this problem. And that equation says the following. If I take a look at my spool, right? So here's my spool, and here's my table. This is connected to my mass down here. This mass has lowercase m. This is capital M. Now, what I'm going to claim right now is that the acceleration of this weight right here, okay, the acceleration of this weight is going to equal the acceleration of the center of mass of the spool plus not only that, but also the acceleration of the spool itself. Okay, and what is that going to be if not r times alpha of the spool, right? So the acceleration of the spool is going to be the radius, this radius right here, times the angular acceleration of the spool. Okay, so what I'm claiming right now is that the total acceleration of this weight right here, is going to be the acceleration of the center of mass of the spool. But not only that, not only the center of mass, but also the acceleration due to the spool itself. Okay, due to the spool unwinding. That rotational motion also has to count for something. Okay, now don't forget, we have translational motion, yes, but rotational motion is also a must. It must be considered in this problem to give you the correct answer. So the additional equation that we're going to need to solve this problem is, in fact, this equation right here. That the acceleration of the weight is equal to the acceleration of the center of mass of the spool plus the acceleration of the spool itself, the rotational contribution to the acceleration. And what is that going to be? Well, we recall that linear acceleration is r alpha. And what is r? Well, r, if I look at my diagram here, right? So this spool has a diameter d, so r is simply going to be d over 2. That tells me my acceleration of the spool is going to be d over 2 alpha. So this is going to be d over 2 alpha. And alpha of what? Alpha of the spool, the angular acceleration of the spool. Okay, wonderful, wonderful. So now we have our last equation of motion, which is going to help us solve this problem. Let me just demarcate each of these equations so that we can notate which equation we're using when. So this is equation 1, 2, 3, and this last one that I just wrote down is going to be equation 4. So wonderful. Now let's go ahead and solve the problem. Okay, remember, what is our goal? What are we trying to solve? We're trying to figure out the velocity. Oh, I guess I erased the lowercase mass. We're trying to figure out the velocity of this small mass once this spool has traveled the distance L. Okay, let me show it in a different way. So let's say this is my spool, this is my lowercase mass. Okay, as the spool is unwinding and it gets closer to the edge, the mass is falling. Question is, by the time the spool has arrived here, what is the velocity of the mass, right? So what's the velocity of the small mass right here, right? That's the question. That's what we're trying to figure out, okay? So we've got all of these equations. Now, what do? Well, the first thing you want to do is work backwards. Work backwards. Here's what I mean. Just remember that velocity is what? Vf is equal to Vi plus At. We assume that the spool, the mass, everything has been released from rest. So this Vi is 0. So we just need A times T. Now, A of what? Acceleration of what? Well, the acceleration of the weight, right? We need the acceleration of the weight times time. Okay, the amount of time it takes for what? The amount of time it takes for this mass to traverse this distance L so that it reaches the edge of the table. But wait a second, we already know the acceleration of the weight, do we not? By virtue of equation 4 right here, right? Well, yes, kind of, but we actually don't know what the acceleration of the center of mass of the spool is, or this angular acceleration of the spool, right? We have to first calculate these, and then once we calculate them, we have to calculate the time and then find the velocities, okay? So now we have a picture in our mind. We have a picture, we have a plan. What's the plan? The plan is to calculate the acceleration of the center of mass of the spool, calculate the angular acceleration of the spool, use those to calculate the acceleration of the weight. Okay, that's one thing. And then somehow we have to calculate the time that it takes for the loop to traverse this distance, okay, the spool to traverse this distance. And then once we get the acceleration and time, we can finally figure out the final velocity, V sub f. Okay, very good. So that's the plan. That's the strategy that I'm going to employ. So let's go ahead and employ it. First thing we're going to do is take a look at this equation. Let's take a look at equation number 2. So I'm going to start writing from here. So hopefully that's visible. So equation 2 states, well, it's just Newton's second law for the large mass. So we have, for the small mass, mg minus t is m a weight. All right. Now, by virtue of equation 3, I can replace the tension T with what? M times the acceleration of the center of mass of the spool. So mg minus capital M A, where A is the acceleration of the center of mass of the spool, and this is equal to M A weight. Okay, wonderful. But I know what the acceleration of the weight is. It's just the acceleration of the center of mass of the spool plus the angular acceleration of the spool. So now I can just substitute that in. So mg minus m, acceleration of the center of mass of the spool, is equal to m times this quantity right here, acceleration of center of mass of the spool, plus d over 2 acceleration, angular acceleration of the spool itself. Okay, so that is great. Now, let's take a look at this equation, equation number 3 and equation number 1. Okay, those are going to help us. Let's erase our strategy here so no one can copy it. So equation 2 tells us what? Let me write that down. Equation 2 tells us what? Well, it tells us that the tension force acting on the spool is m times the acceleration of the center of mass of the spool. And equation 1, we haven't used that one yet. Maybe we can extract something from there. Equation 1 tells us that the torque is equal to 1/2 times the diameter of the spool times the tension, and that's equal to the angular acceleration, moment of inertia, times the angular acceleration of the spool, right? Now notice something. If I go ahead and multiply equation 2 by 1/2 d, then I should get equation 1, right? So in other words, if I go ahead and multiply both sides here by 1/2 d, 1/2 d, then this should be the same as equation 1. And equation 1 is equal to the moment of inertia times alpha, the angular acceleration of the spool. So this should equal the moment of inertia times angular acceleration of the spool. Right? No harm, no foul. So now I can go ahead and exploit this to figure out some important quantities. First thing I'm going to do, I'm going to write 1/2 dt, okay, is equal to m time. Well, actually, let's move that 1/2 factor out to the front. So I have 1/2 md, acceleration of the center of mass of the spool, is equal to, now what's the moment of inertia of a spool? Well, that is a good question. Well, you may recall that the angular, the moment of inertia for a disk is 1/2 mr squared. Okay, so I can just plug that in. This is going to be 1/2 mr squared alpha spool. Okay, great. So now let's take a look. What is r? R is simply d over 2. So I'm going to write 1/2 m d over 2 squared alpha of the spool. So this is going to be d squared over 8 m times the angular acceleration of the spool. Okay, and all of this is equal. Hopefully you can still see this. God, is it just on the edge of the screen? Well, apologies. So, relationship between the two accelerations, okay? So, what do I mean? Let's find out. The m's cancel out, okay? This 1/2 makes this 8/4. This d cancels out with one of the d's. So that means the acceleration of the center of mass of this spool is simply d divided by 4 times the angular acceleration of the spool. Okay, this is going to be very handy. This is going to be very handy. Okay, so let's keep this equation that we just derived in mind. And let's come over here to this equation. Now we have an equation in the acceleration of the center of mass of the spool and the angular acceleration of the spool. But we also have an equation relating these two variables, these two accelerations. So we can individually solve for each acceleration and then plug them in. Okay, that's the idea. That's the idea. So let's do that. What I'm going to do is replace, let me tap this red marker. What I'm going to do is replace this acceleration of the center of mass with what we just calculated. D divided by 4 times the angular acceleration of the spool. Or actually, you know what? It might be easier. Let's first calculate the other one first, because that'll be way easier. Then I don't have to substitute for two things. So d over 4 times angular acceleration of the spool is the center of mass acceleration. So d over 2 is just twice that, is it not? Is it not? So this is simply 2 times the center of mass acceleration of the spool. Why is it 2 times? Well, if I multiply this by 2 here and this by 2 here, then this will be d over 2 angular acceleration, which is exactly what I have here. Okay, so now let's see what I get. So 2 times the center of mass acceleration plus 1 of that is just going to be 3m, right? 3m acceleration of center of mass of the spool. Hopefully you can see down here. And that's equal to mg minus ma center of mass of spool. So now I'm going to just go ahead and solve for the the center of mass acceleration. So let's bring this over to the other side. So I'm going to have, factoring out the center of mass acceleration of the spool, I'm going to obtain 3m plus capital M is equal to mg. And then just solving for my acceleration for the center of mass, I obtained that the center of mass acceleration for the spool is equal to mg divided by 3m plus capital M. So huzzah, there we go. We have obtained one of our two accelerations. Very big deal indeed. Okay, very good. And now we just have to figure out our other acceleration. But hey, we already know what it is, right? It's right there staring at us in the face. If I just solve for the angular acceleration of the spool, then I'm just going to obtain 4 times mg divided by, this d is going to go to the bottom, 3m plus capital M. And voila, this is the angular acceleration of the spool. So now I've obtained both accelerations, and now I can go ahead and plug them in right here. Okay, and now if I do that, let's go ahead and do that. Let's see what we get. What should I erase? Let's erase this. We don't need this anymore. By the way, if you're wondering, I'm going kind of fast. Please feel free to ask any questions down below. This is usually the pace that a Brown University class goes at. So if you can't keep up, it's your problem. Okay, so let's go ahead and plug it in right here. So this is equal to the acceleration of the weight is equal to the acceleration of the center of mass of the spool, which is this thing right here, mg divided by 3m plus capital M plus d over 2 times the angular acceleration of the spool, which is what we just computed here, 4mg divided by d 3m plus capital M. So now let's cancel out the things over here. Okay, so this works out to be what? 2mg plus mg is 3mg divided by 3m plus capital M. Okay, so that is the acceleration of the weight. Finally, good Lord. So this is the acceleration of the weight. Okay, this is what we've been after for so long. But there's one more thing, right? We've got to calculate the time it takes for this spool to traverse this distance L right here. So how do we calculate that time? Well, use your best friend. Okay, your best friend should be none other than d is equal to VIT plus half AT squared. Of course, this whole system starts from rest, so d is simply half AT squared. Now, the question is, this gets a little tricky. Which A should I use? Well, think about it. I just want to know how much time it takes for this guy to traverse this distance L. So should I not use the acceleration of the center of mass of the spool? I'm not going to use the angular acceleration of the spool because that doesn't make sense. That calculates how fast this thing is rotating. I don't want to know that. I want to know how fast this thing is linearly translating, how fast it's moving translationally, right? Because I just want to know how much time does it take to traverse this distance L. So what I care about is not alpha spool. No. That tells me how fast this thing is rotating. I care about the acceleration of the center of mass of the spool. This is what I care about. So let's go ahead and plug that in. So distance is equal to 1/2 the acceleration of the center of mass of the spool times t squared. Now, what's the distance this thing is traversing? Well, it's just this distance L, right? So this distance d is simply L, okay? And let's go ahead and solve for t over here. So t is going to be 2L divided by the acceleration of the center of mass of the spool, and this whole thing square rooted. So now, what is the acceleration of the center of mass of the spool? Well, we calculated that here. Just flip it over, flippity dip dip. So that is going to be 2L times 3m over m, 3m plus m over mg. All right, so there, right there, that is the time it takes for the spool to traverse the distance L. So now that we have that, right, now that we have the time, now that we have the acceleration, all we have to do is child's play, okay? Now even a baby can figure out the answer by using, oh, did I throw it at the camera? Well, apologies. Now even a baby can figure out that the final velocity is acceleration times time. The acceleration of the weight is 3mg divided by 3m plus capital M, and multiplied by this time right here, 2L times 3m plus capital M, all divided by mg. And ladies and gentlemen, this is the final velocity of the weight after the spool has traversed the distance L. How powerful is that? Isn't that shocking? If you are not genuinely amazed by the fact that, we were able to use pen and paper, pen and whiteboard to calculate something in real life, to predict something in real life, then I have no words for you. Then you probably have no emotion, because I mean, this has got to be shocking, right? We just used basic math to figure out something that's true about the real world. and that's the power. That's the visceral power of physics. So this problem was mostly elementary. There was nothing crazy about this problem. Just use Newton's second law, you get the answer. So hopefully this was straightforward. If you have any questions or comments, please put them down below, and I'll see you in the next one.